Hey guys, welcome to the fifth video of the series Algorithms in JavaScript. So this is the video in continuation of the previous video of the graph algorithms, which in that video I talked about the DFS algorithm and the basic idea of what the graph is, right? So in this video, we'll talk about DFS. So if you haven't seen that previous video, which is about graph and the BFS, please do watch it and come here again, right? So what is a DFS? So DFS, which I already told you multiple times, which is depth first search. Okay, so I'll talk about which data structure we use to solve this algorithm. Similarly, like in the BFS, you remember we were using a queue data structure to solve that algorithm, right? Solve problems with that algorithm, right? In the implementation of that algorithm. So in the implementation of a DFS algorithm, we'll be using a data structure called stack. Okay, so let's first understand what is depth first search. So you already know what a graph is, right? So depth first search, which literally it means we have to search for depths first. Depths, we have to search for depths first, right? We have to prioritize searching for depths first, right? Okay, so we are talking about depth. So remember, I told you in the previous video, while implementation of the BFS is always imagine a queue as a straight line, because it was a breadth for search. And whenever we talk about breadth, we imagine things in a straight line horizontally. So that's how you remember in the breadth for search, you use a queue because it's a breadth. Queues are straight, not vertical. So whenever you try to implement algorithms using DFS, that's depth for search, you always remember it is about depth. It is about searching in depths. So a stack is always a depth thing. A stack is always represented vertically. You cannot put a stack of books horizontally. You wouldn't call it a stack, right? Stacks are always vertical. So multiple books are placed on each other one by one, right? So that is a stack. We call that a stack of books. That's why we call that a stack of books, because it is vertical in nature. It has a depth from top to bottom, right? It has a depth from top to bottom. That's why depth for search is called depth first search, right? We have to search along depths, and that's why we use stack data structure. Because we have to search for depths. You remember, this is the way of remembering, nothing related to concept, but this is a way of remembering. Like in DFS we use stacks. That's how you can remember. If you want to take my advice, that's how you can remember very easily. Like depth means stack, because in a stack is always represented vertically, and vertical stacks have depths, right? Now let's try to understand the implementation, right? First, so you remember, so you should be already knowing, right, what a stack is, right? A stack is a data structure which is last in first out. So I'll tell you in a real world scenario why it is called last in first out. Okay, whoever comes last will go first, right? Why it is called? Let's say you have a bunch of books, stack of books, right? Okay, so you try to imagine yourself, which book will you remove first, or which book can you remove first? The top one, right? But did you see the top book came at last? You put the first book initially, right? And then the second book, then the third book, then the fourth book, then the fifth book, then the sixth book. The sixth book came at last. It didn't came first. So this is the first book, but we are not removing that. We are not even able to remove that because it is heavily put down by these books. It has a heavy weight of these books. It is carrying the heavy weight of these books. It is quite very difficult to remove this book, right? So we'll do the easy thing. We'll remove the top one. then we'll remove the next one, then we will remove the next one, then we will remove the next one, then we will remove the next one. We will keep doing this until our stack is empty, until we have no books in the stack, right? This is the same thing what we have to do while implementing the DFS technique. We have to keep removing the elements of a stack, right, until our stack is empty, right? And we have to keep the search for our books. Let's say I'll tell you, I tell you, please give me the fifth book from the stack, right? How we'll do that? You search 3, 4, 5. The fifth book is at the bottom of the stack. So what you'll do, you'll remove the stack of books. You'll remove one book from the top, another book from the top, one by one, until you reach to the fifth book in the stack, right? You'll see if the stack is, if you have reached till that book, and if you want to take the last book of the stack, you have to make the stack empty, right? So that's how you implement the DFS algorithm also. A stack is a last in first out data structure. Let's say we have a graph which is A, B, C, D, okay, and A. So let's start from A, okay? Similar to the queue, right? What we do, we just push some data, right? Okay, but there's a difference. In the stack, we push from the top, we pop from the top, but in the queue, what we were doing is we are pushing from the back and popping from the front, but not in this case, right? Okay, now we are starting from A, we just pull A, go the depth of A. Okay, now the depth is B, C, E, B, C, E. Okay, cool. Now what we will do is we'll now remove E. We have to go the depth of E. E doesn't have any depth, right? E is already, it doesn't have any children, it doesn't have any siblings, it doesn't have any adjacent nodes, right? So we cannot go more down. So now we'll try popping C. We'll try to go depth of C. Okay, there is only one path from C to E. E is already traversed, so there is no way we can go depth C. Okay, now it's pop B. Now what we should do is, there is a path from B to C to E, right? You saw, but C and E are already traversed, right? There isn't any node left, right? Okay, so there is only one node left, which is A has also a path. Always remember, A had a path from A, B, C, E, but A has also a path from A, D, C, E. But you remember, D, C, E. C, E is also already traversed, but D is not traversed. You can put D here. Our stack is empty, right? So we have a DFS of our graph, which is A, E, C, B, D, right? 5 elements are covered, right? So let's talk about the code part of this graph. So the stack data structure, right? DFS is implemented using the stack data structure, and the DFS algorithm can be implemented in two ways, unlike BFS. So ways, which is an iterative method and a recursive method. So I'll tell you an iterative method first, because we haven't talked about recursion here, which I'll surely talk about in next video in detail, what a recursion is, how it works behind the scenes, what goes under the hood. But for now, let's just try to understand a recursion is a function, a phenomena when we call a function again and again in order to get a result, and we should have a exit case for a recursive function, exit case, right? We should have a exit case for a recursive function, so that we don't get stuck in an infinite loop, infinite recursive call stack. Okay, so we should always have an exit case for a recursive function. First, let's just talk about the iterative method. So similarly, we have our graph relations similar to the PFS, which is an adjacency list, which is my preferred choice. So irrespective of any input you get in any question, just try to visualize your graph and convert that graph to an adjacency list in the form of map, right? And then solve the problem, right? It would be very easy and very time efficient also. So let's start from the A, similar to that. And now let's just see, we started from the stack with the first element. Likewise, we'll keep doing the operation until our stack is empty. Okay. Okay. So this loop will not run if our stack is empty. So we will keep doing this operation until the stack's length is greater than 0, not empty. So we'll pop from top. There's a current element. We try to loop over all the elements, all the neighbors. Okay. All the neighbors of our stack, right? And we push the elements in a stack, right? Elements in a stack. Okay. Now this will give the same result. Okay. Let's try compiling that. So A, C, E, B, D, F, right? So if you see, this came to be A, C, E, B, D, F. You see, this is different than that BFS, right? You see, there should be a relation. So let's try visualizing this. So what is happening? Everything is happening from top, right? We are pushing the things in the stack from top, popping from top. That's why. Okay. So if you try visualizing this, this is a A, this is a B, C, D, A, F. Okay. There's a relation between A, there's a path between C, B and D, sorry, my bad. Reverse this in order to make it look better. Okay. So there's a path between B and D, there's a path between C and E, there's a path between D and F. There isn't any path from A and E and F. Okay. Now let's just visualize the output. A, C, E, B, D, F. How did it came? So we have our stack, right? We started from A. Okay. We started from A, we'll go across depths, right? So we pull down the A, we pop the A. Okay. We'll push. Okay, the neighbors, will iterate over the neighbors of A, B and C. Push the B and C. Okay, now we'll pop the C. Okay, we'll iterate over the neighbors of C. C's neighbors are only E, right? We'll push them. We'll pop the E. Okay. Now we'll iterate over the neighbors of E, which are none. Okay. Now what we will do, we'll pop the B. We'll push the neighbors. Neighbors are D. We'll pop the D. We'll push the neighbors of D, which is F. We'll pop the F. push the neighbors away, which are none. A, C, E, B, D, F is the sequence, right? Similarly, you saw here also, we started from A, okay? We pulled the A, we push the neighbors of A, which are B and D, okay? Sequence could be different, right? So sequence could be different. I told you there are multiple sequences which are correct. So this can be the sequence. We have the A, now we pop the D, and D's neighbors are C and, okay, only C. Push, we'll pop the C. C's neighbors are E, okay? So we'll pull the E, we'll pop the E. E's neighbors are none. We'll pop the B. B's neighbors are C only, which is already visited, okay? So what is remaining? A, B, C, D, E. There are 5 elements. This is our sequence, A, D, C, E, B. 1, 2, 3, 4, 5. A, D, C, E, B. This is our stack is empty, and our final DFS of this graph is this, ADC EB. Okay, there could be multiple ways. This sequence can change based on what element you take first, what in what order you push into the stack, right? This sequence can change, but the fundamentals will remain same, right? But the fundamentals of depth first search will remain same. So ADC EB is the sequence for this 5 nodes, 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, cool. So thank you so much for watching the video, and stay tuned for the next set of videos. And in the next video, we'll talk about the recursion and how it works under the hood, and we'll visualize the recursion tree. Okay, we'll visualize the recursion tree also in order to understand the recursion better, right? So we'll talk about the recursive approach of depth first search in the next video, in the recursion video, because in that video it would make more sense. This solution would make more sense in that video. So I'm not discussing this here. Thank you. Thank you so much. Thank you for watching the video, and hope you liked it. If you liked it, please do subscribe and press the bell icon. Okay, and stay tuned for the next videos in the playlist. Okay, thank you so much, guys.